Hey everyone, so we are now moving into chapter 4. Chapter 4 is applications of derivatives. So this is pretty a long chapter. Like chapter 3 we went through chapter 3 really fast. Chapter 4, we're going to be in this chapter for a while. It takes us a while to get through everything. Okay, so pause and do the do now. All right, so f prime equals 7 plus 1 over x, plug in 1, and we get 7 plus 1, so we get 8e. That's it. Okay, so we are working on word problems called related rates problems. So related rates, so rates that are related. So they're problems involving the changing of multiple variables with respect to time. But they're not changing at the same rate, right? Like slope of a line, like the cars are driving, and the rates are very specific. But when you're looking at like a three-dimensional figure, like a balloon, the radius is not changing as at the same rate that the volume is, right? When things change, it's not the same. When different parts of something are moving, it's not the same. And I have some visuals I'm going to show you in class. Okay, so we're going to suspend reality for a second and pretend that a balloon is a perfect sphere. We all know it's not. It's like a weird shape, but just for these problems, we're pretending, just like in lower level problems, we have to pretend that things are actually as nice as they are. So we are blowing up a balloon, and the balloon is inflated at 10 centimeters cubed per second. How fast is the radius changing when the diameter of the balloon is 1 centimeter, 2 centimeters, and 4 centimeters? So we need some kind of formula. What formula do we know that involves a sphere? And then a good hint here is inflated at 10 centimeters cubed per second. What does that rate? What rate is changing there? That's the volume of the balloon. So we should know, the volume of a sphere is 4/3 pi r cubed. All right? If you don't know that, you need to know that. It wants to know how the radius is changing. So things that we look at, we need the initial, and then a lot of times we need the derivative. So when we're doing these problems, you really want to think of it as implicit. So if we have v, its derivative is dv dt, because we're doing things in terms of time, not x. If we have r, then it's dr dt. Right? So what would be the derivative of the volume? So dv dt equals 4/3 pi, and then what's the derivative of r cubed? 3r squared dr dt. And then the nice thing with this one is those 3's end up canceling. So we get 4 pi r squared dr dt. So this is our derivative. So now what are these numbers they gave me? They gave me 10 centimeters cubed per second. What is that? That's my dv dt. Right? How fast is the radius changing? So the radius changing, that's your dr dt. So this is my question mark. When the diameter, so now that we're going to fill in, we're going to have a few different problems. The diameter is 1. So if my diameter is 1, then what's my radius? A half. If my diameter is 2, my radius is 1. My diameter is 4. My radius is 2. So we're just going to plug in and solve for dr dt. So there are 3 different problems here. So dv dt, we figured they told us was 10. 4 pi. So I'm going to start with my 1/2, right? Start with that first one. 1/2 squared dr dt. So then we're going to solve for dr dt. So dr dt equals, that becomes, it's just 10 over pi. right? 4 times 1/2 squared, cancel out, so we divide both sides by pi. That's it. So for this one, dr dt is pi over 10, 10 over pi, just kidding. And then, I don't have a lot of space here. Now let's do r equals 1. So 10 equals 4 pi, 1 squared dr dt. So this time dr dt equals 10 over 4 pi, or 5 over 2 pi. And then the last one, if r equals 2, 10 equals 4 pi times 2 squared. So dr dt equals, what's that, 16? 2 squared is 4, 10 over 16 pi, which is 5 over 8 pi. Right. So that's the process here. This is a pretty straightforward one. There's not a lot to do. Again, this is the very first one we've done, so. Okay. This is more of a typical one that we will do. A 6-meter ladder is leaning against a wall. All right, I'm going to draw a picture. Here's my wall. Here's my 6-meter ladder. It's 6. Is leaning against a wall if the bottom is pushed out at a constant rate. So this bottom is going out at 1/2 meters per second. How fast is the top of the ladder? So the bottom of the ladder is sliding out and then the top is going down. So that's our question mark. How fast is the top of the ladder sliding when it is 5 meters up the wall? So they're giving me up the wall is 5, right? All right, so again, the first thing you need to do is identify what's the equation we're going to be using here. So we have, what does that look like? We have a triangle leaning up against it. Its buildings are 90 degrees. So we're going to use the Pythagorean theorem. So you can use x, y, z, a, b, c, it's up to you. So a squared plus b squared equals c squared. So now the first thing I typically do is I'm going to make myself a little table over on the side. Right? I have my a, and then I need dA dt. I have my b, dB dt. And then I have my c, dC dt. I didn't do that on the other one because it was a little more simple. All right, so now identify which letter is which. So 6 is my C, so I know 6 is C. A and B doesn't matter, so just pick something. So let's see. I'm going to make this one my A and this one my B. So in this case, my B is 5. And what else do I know? I don't know A, but I do know dA dt, right? This is my changing, so this is 1/2. So we have 3 things missing, but what are we finding? This is my question mark, all right? So that is the thing that we need. So now we have to figure out, can I figure out what A is? Well, it's the Pythagorean theorem. So now let's plug into the Pythagorean theorem with my 5 and my 6 and figure out what is my A value. So I've got A squared plus 5 squared equals 6 squared. So 25, plus 25 equals 36. So A squared is 11, so A is root 11. All right, so I'm good there. Now, dC dt, I don't have that either. So think about, what does that represent? It's the changing in the size, right? So as the ladder moves out, right, over here, as this goes out, this distance is changing and this distance is changing. Is the ladder changing? Is the ladder getting bigger as it goes? No, the ladder is consistent. So its rate of change would be what then? 0. The rate of change of my ladder is 0. That's really important. Something you want to pay attention to when you do these problems. Sometimes one of the variables has a rate of change of 0 because it can't change. Right? That ladder isn't just randomly getting longer. All right, so now we have all our information. We have our little chart filled out. So now I'm going to go through, we're going to take our derivative. So I have a squared plus b squared equals c squared. Use implicit differentiation and find the derivative. Derivative of a is 2a dA dt. This is not going to work out for me. Okay. I'm going to erase this so I have more space, because this is not going to fit. All right. Plus 2b dB dt equals 2c dC dt. Now, one thing you can do, you can cross all your 2's out if you want. You can leave them. It's up to you. Now I'm going to substitute in. So I've got 2. A is root 11. dA dt is 1/2. 2. B is 5. I'm solving for dB dt. And 2 times 6 times 0. So that's 0. So over here, the 2 and the 1/2 cancel. So I have root 11 plus 10 dB dt equals 0. So dB dt equals negative root 11 all over 10. And that's my answer. I don't want decimals. All right, now it's negative. Is that a problem? Is it a problem that that rate is negative? It's not. And here's the reason. Think about it. As the foot of the ladder is going out, right? This side is getting bigger, so my rate is positive because that size is getting bigger. As this is going down, what's happening to this distance? It's getting smaller and smaller. So that's something you want to keep in mind when you're doing these problems. The negatives do matter. So if something is increasing, the rate should be positive. If something is decreasing, the rate should be negative. All right. This is a very, very common problem. Probably one of the most common problems we do. We see these a lot. I guess all of them. I'm really just doing the intro problems today. So, okay. Water is flowing into a cone that has a height of 16 centimeters and a radius of 4 centimeters at 2 centimeters cubed per minute. How fast is the water level rising when it is 15 centimeters deep? All right, so here's my cone. All right, what's our formula? Who knows the volume of a cone? 1/3 pi r squared h. All right. The cone, now here's the tricky thing with this one. They're giving you multiple things. So they say the height of the cone is 16 and its radius is 4. So we have this 4 and this is 16, right? Water is flowing in at 2 centimeters cubed per minute. How fast is the water level rising when it's 15 deep? So we know the height is 16, but then they're also giving me 15. So what are we going to do there? So that's a little tricky. So they want to know, I'll make it blue for water. So they're also telling me that this is 15. So we have two heights, which is going to be a slight issue. And then they want to know, so we have V dV dt, R dr dt, and H dH dt. All right, let's see what they gave us. So they gave me dV dt, which is 2, right? They gave me, what do they want to know? How fast is the water level rising? So that's dH dt when it is 15 centimeters deep. Now, here's the thing with the 16 and the 4. That's the entire, giant cone. It's not the actual water, and here's the issue. We can't put 4 here. And just as we can't put 16 here, because that's not the height and the radius of the water. That's of the entire container, right? So notice we have no information about dr dt. We don't know the volume, but we don't really need the volume because when you take the derivative of v, it's just dv dt. So you never, that's a really common thing where you don't know your v. So here's why they gave that to us. We don't know the radius. So here's what we're going to do. We are going to use that 16 and that 4, and we're going to make a proportion. Right? So radius over height equals, or you can do height over radius, it really doesn't matter. The radius was 4 and the height is 16. There's a proportion, these are in proportion, they're similar cones. So I'm going to set up a proportion, cross multiply, 16r equals 4h. And then I'm going to look into my problem. Which one do I not have information about? Which one do I not care about? I don't care about r, right? I want to get rid of r. So I'm going to solve for it. R is 1/4 h. So then what we're going to do is we're going to take that and we're going to plug this into our equation. We want to get rid of one of the variables. We're getting rid of one of the variables. So v equals 1/3 pi. Instead of r, I'm going to replace it with 1/4 h. My pen turned off. Squared h. So we figured out a proportion between the water and the cone. We used that proportion, cross-multiplied, solved for the one that we don't care about, and replaced to get rid of it in the formula. So this is 1/16h cubed, h squared. So we end up getting 1/48 pi h to the third, and that's our volume formula we're going to differentiate. Because we really want to avoid also a product rule. If we just take the derivative of the original formula, we would have 2/3 pi r dr dt h plus 1/3 pi r squared dh dt. You'd have to do a product rule, but we don't have enough information. So now we have this, we can take the derivative. See if I can fit this all in. So dv dt equals, I'm going to bring my 3 down, pi h squared dh dt. So my dv dt was 2. I'm going to change 3/48 to 1/16. Pi, they gave me h was 15. 15 squared dh dt. So we get 16 times 2 is 32 over 225 pi equals dh dt. And that's your answer. This is rough. I understand that this is rough. Plus my work was a little ridiculous. I apologize. This is a hard problem the first time you see it. We're going to do like 5 more of these, so you will get better at them. But it's really, really common if our formula has more than one variable in it. A lot of times we're going to do these, especially cone problems. This is pretty common for the cones. Okay, last problem. A baseball diamond is actually a square with sides of 90 feet. So I'm going to draw myself my square. So here's my baseball diamond. So these are all 90. A runner in a baseball game runs down the third base line. So he's running. He's here. This is third base, right? And he's running this way. He's running down the third base line at 20 feet per second. How fast is the distance from second base changing when he is 10 feet from home plate? So he's here. He's 10 feet from home plate. Here's second base. All right. So what shape are we dealing with here? It's a square, but it's not a square. Because we have this diagonal in here, this is a right triangle. We're going to do Pythagorean theorem again. All right. So this is my C. I'm going to make this A, this B. Doesn't really matter. So I have A, dA dt, B, dB dt, and then C, dC dt. All right, I want you to go through and see what you can fill in. Just fill in as much as you can. All right, so B is my 90. What's A? So there's actually two questions here. Let's just we'll focus on the 10. When he is 10 feet from home plate, so this is 10, which means he's at 80. Right. He runs down the third base line. So that's dA dt is 20. All right, okay, so now we don't know C, we don't know dB dt, and we don't, we actually know one of those three. Which three do we know? dB dt is not changing. So the thing that's this piece right here is always 90 and it's not going to change. This distance is changing and like this is going like that, so it is changing also. So dB dt is 0. And then it's asking us how fast is his distance from second base changing. So that's our question mark. Right? And then what are we going to do to find C? Pythagorean theorem. So a squared, 80 squared plus 90 squared equals C squared. Let's see. 90 squared is 14500 divided by 100. Let's see, 14. I can divide by 900. Oopsies. 14500 divided by 900. Nope. $145? Does that not have a perfect square that goes into it? All right, well, I'm just going to write C is 10 root 145. That's good enough. Okay, so now I have that's my C, 10 root 145. All right, so now we're going to go through and do the Pythagorean theorem, the derivative of the Pythagorean theorem. So a squared plus b squared equals c squared. 2a dA dt plus 2b dB dt equals 2c dC dt. So this is why I like making the chart, because I know what once I fill it all in, it's just not as bad. All right, so 2 times 80 times 20 plus, that's 0, equals 2 10 root 145 dC dt. So dC dt equals, let's see, the 2's cancel, 10 goes into 20, so we get 160 over root 145. That's our answer. We don't have to do the 45. If you want to pause it and try it on your own, go for it. It's good practice, but it's the same process. Okay, so here's the breakdown of what we're going to do here. We identify the equation that we want to use for this specific problem. If possible, we substitute into the equation one variable in terms of the other. So that's in your cylinder. Basically, for cylinder problems, I would say we substitute in 90% of the time, 95% of the time, a lot. Plug into the original equation to find any necessary variables. So we need to use Pythagorean theorem to find the missing piece. Once you get all those variables set, we differentiate using implicit, and then we plug in and solve for the unknown rate. Here's your homework. Notice there's only 5 problems. This is hard. Like, I know this is hard. I want you to just, if you can't, just do the best you can. We're gonna spend the entire class on Wednesday going over homework. Like that's what this unit is, this mini like section is, where it's you guys struggle and then I help you through it. You struggle, I help you through it, and then eventually you get it. All right. This is gonna be challenging. I know that, but you can do it. I promise. You will get there. I'm also giving you additionally to this homework, there's a worksheet and I want you to just do half of it, right? And then on Wednesday, I'm going to assign the other half.